Hi, my name is Yue Mao. Today I'm going to present our work, Extrinsic Dexterous Manipulation with the Direct Drive Hand, a case study. Assembly is a very common task for industrial robots. A complete assembly process consists of three major steps: singulation, acquisition, and assembly. The first step, singulation, means separating a component from a pile and identifying its pose and position. And the final step apparently means assembling a component into a system. Our work focuses on the middle step. When we say acquisition, we mean a component is grasped by a robot hand at a specific pose so that it can be assembled successfully. As the component can be at any of the stable poses after singulation, such a proper grasp is not always feasible due to manipulator and environment constraints. To address this issue, researchers have taken different approaches in the past decades. Here's the simplest method called place and pick. The object is picked up, placed in an intermediate pose, and picked up again, so on and so forth until it's ready for assembly. This tends to be very slow, as multiple grasps and large arm motions are required. Salisbury introduced the concept of dexterous hand in 1982, which does in-hand grasp of objects. To achieve a high degree of dexterity, such hands need multiple contact points with the object, each has multiple degrees of freedom, which results in a large number of actuators required. These designs are brilliant, but such high mechanical complexities may not be practical in industrial applications, considering factors such as ease of maintenance. We want to make acquisition efficient and simple, so we explore a new kind of dexterity, extrinsic dexterity. That is, we consider the table surface as a third finger. If a component starts at a swivel pose different from its assemblable pose, we first use the roll of fingers with the help of table surface to reposition the component, and then do the final grasp. That being said, we've broken the problem down into the transition between poses. In our paper, we deal with the task representative of challenges faced by industry. Assemble the small, medium, and long bumper into a housing to form a sub-assembly of an automotive door latch. These small components have multiple stable poses, and their geometric configurations and material properties vary, which adds on to the difficulty of acquisition. As an example, here's a slow-mo video of how we use extrinsic dexterity to reposition the medium bumper. We carry out the task with the system in the image. A robot hand is attached to an ABB IROS 120 manipulator to execute the manipulation. A vision system includes a camera looking from the top and a transparent table with a computer monitor underneath to provide high contrast between the components and background. Motion planning and control subsystems, together with inter-process communication, are also implemented. The robot hand we use is a direct drive hand, which we call DD hand. It's an end effector system developed at the manipulation lab. It has a low payload, fast cycle time, and high robustness, and operates in a single plane at a time. Coming back to the pose transition, we simplify the process by recognizing that if we identify a suitable 2D plane, we can reposition the component simply along a trajectory in that plane. We've designed two primitives for this purpose: pivot and topple. When executing these primitives, a fingertip gets in contact with the component and then moves along an arc to rotate the component, which results in a stable pose change. For the bumpers we deal with, most of their stable poses are just one step away from their final poses using pivot or topple. However, there exists a special case. If the long bumper starts at pose 1, it requires a 180-degree rotation to get to its assembled pose, pose 0. Such a rotation can't be done with one single pivot or topple due to contact point restrictions. Therefore, two consecutive primitives are executed. This case reviews a new problem beyond the execution of primitives. Here's a video and a time block for this two-transition manipulation. As you may notice, the motion that takes the longest time is not the primitive, but vision detection and arm motion. This is because we rely on the vision system to do between transition pose detection, so that we can execute the second primitive accurately. To do that, we have to move the arm out of the camera's field of view, call the vision system, and then move the arm back. Getting rid of this time-consuming step, open-loop execution is a method we'd like to explore. Ideally, the vision system is called only once at the start to inform the robot about the component's starting state, and then the robot completes multiple transitions purely based on predictions of the component's states. To implement this idea, we need to overcome the propagation of uncertainty. Two other primitives, push and squeeze grasp, have been designed to serve this purpose. The push involves motion of one fingertip along the ground plane through a component's initial position, and the squeeze grasp is defined as two fingertips approaching the object from opposite directions and applying a squeezing force, which is also used for the final grasp. Throughout the execution of these primitives, the component is in contact with the fingertips. As we know where the endpoints of fingertips are, we can have an accurate prediction of the component's position. This experiment demonstrates the effectiveness of push. As you can see, after two transitions, the propagated error is significant. Adding a push in the x direction leaves the uncertainty in y direction only, and adding pushes in both directions makes the uncertainty negligible. In conclusion, our work makes strides towards improving the acquisition process in simplicity and robustness. While we have provided a nice solution for a specific real-world application, moving forward, we are looking to improve our work in two main directions. First, the exploration of primitives. Are the ones we've designed exhaustive? Are there better ones? These questions remain to be answered. Second, automatic motion planning and control of primitives. In our current implementation, we've manually parameterized primitives and ordered their execution. To reconfigure the system for a new object, we only need its geometric information to redo these two steps, which is not hard, but there are definitely more efficient ways we would like to develop. For instance, auto-generation of primitives. That's all of our presentation. Please don't hesitate to email us if you have any questions. Thank you.